Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the autumn of 1882, a 17-year-old boy climbed a cherry tree in Worcester, Massachusetts, and experienced what he would later call his moment of cosmic revelation. Robert Goddard gazed upward through the branches at the stars and imagined himself traveling among them. This wasn't mere childhood fantasy, it was the birth of modern rocketry, though the world wouldn't recognize it for decades. Goddard's fascination with spaceflight intensified after reading H.G. Wells' The War of the Worlds. While others saw science fiction, Goddard saw engineering challenges waiting to be solved. By 1909, as a physics professor at Clark University, he began developing the theoretical framework that would revolutionize space propulsion. His mathematical proofs demonstrated that rockets could indeed function in the vacuum of space, contrary to prevailing scientific opinion. The concept seemed absurd to most scientists of the era. The New York Times famously mocked Goddard in 1920, claiming that rockets couldn't work in space because they had nothing to push against. This fundamental misunderstanding of Newton's third law of motion, that every action has an equal and opposite reaction, would haunt Goddard throughout his career. Yet he persisted, driven by calculations that proved rocket propulsion was not only possible, but inevitable for space exploration. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Goddard's breakthrough insight involved liquid fuel propulsion. While solid fuel rockets had existed for centuries, primarily as weapons and fireworks, they offered limited control and efficiency. Liquid fuels, however, could be precisely controlled, throttled, and optimized for specific missions. His theoretical work identified liquid oxygen and gasoline as promising propellants, though the engineering challenges were formidable. The first liquid-fueled rocket launch occurred on March 16, 1926, at his aunt's farm in Auburn, Massachusetts. The rocket, nicknamed Nell, stood merely 10 feet tall and weighed just under 7 pounds empty. Fueled with liquid oxygen and gasoline, it reached an altitude of 41 feet and traveled horizontally for 184 feet during its 2.5-second flight. While these numbers seem modest, the scientific significance was revolutionary. Goddard had proven that controlled liquid propulsion was achievable, establishing the fundamental principles that would eventually carry humans to the moon. The rocket incorporated innovations that remain essential today: gyroscopic stabilization, liquid fuel injection systems, and combustion chamber cooling techniques. The physics underlying liquid propulsion involves the rapid combustion of fuel and oxidizer in a controlled chamber, creating high-pressure, high-temperature gases that expand through a nozzle. The expanding gases accelerate to supersonic speeds, generating thrust according to Newton's laws. This process, known as the rocket equation, determines the relationship between fuel mass, exhaust velocity, and achievable speeds. Goddard's early experiments revealed critical engineering challenges that would define rocket development for decades. Combustion instability caused engines to explode unpredictably. Fuel pumps required incredible precision to deliver propellants at the correct ratios and pressures. Heat management became crucial as combustion temperatures exceeded 2,000 degrees Celsius. Despite these challenges, Goddard continued refining his designs throughout the 1920s and 30s. His rockets gradually achieved higher altitudes and demonstrated improved stability and control. He developed guidance systems, parachute recovery methods, and even primitive autopilots. Each flight provided data that advanced the science of rocketry, though recognition remained elusive. The scientific community's skepticism gradually gave way to curiosity, particularly as military applications became apparent. Goddard's work laid the theoretical and practical foundation for all subsequent rocket development, from intercontinental ballistic missiles to the Saturn V moon rockets. His vision of space exploration, born in a Massachusetts cherry tree, had begun its transformation from dream to engineering reality. While Goddard labored in relative isolation in Massachusetts, across the Atlantic Ocean, European minds were converging on similar revolutionary ideas about spaceflight. The most influential was Hermann Oberth, a German-Romanian mathematician, whose 1923 publication, The Rocket into Planetary Space, provided rigorous mathematical proofs for space travel feasibility. Unlike Goddard's secretive approach, Oberth sought to inspire a generation of engineers and scientists. Oberth's work went beyond theoretical calculations to practical engineering proposals. He described multi-stage rockets, space stations, and even interplanetary missions with mathematical precision that amazed contemporary scientists. His calculations demonstrated that achieving Earth orbital velocity, approximately 17,500 miles per hour, was theoretically possible using chemical rockets. Though the engineering challenges were immense, the publication sparked enthusiasm across Europe, particularly in Germany, where spaceflight captured the imagination of engineers, writers, and dreamers alike. In 1927, the Verein für Raumschifffahrt, or VFR-DU, the Society for Space Travel, formed in Breslau, bringing together individuals passionate about making spaceflight reality rather than fantasy. Meanwhile, in Russia, Konstantin Tsiolkovsky had been developing similar concepts since the 1890s. Though his work remained largely unknown outside the Soviet Union, Tsiolkovsky derived what became known as the rocket equation, the fundamental mathematical relationship governing all rocket performance. His equation demonstrated that achieving high velocities required either extremely high exhaust velocities or massive amounts of fuel relative to payload mass. The rocket equation, expressed mathematically, shows that the change in velocity equals exhaust velocity multiplied by the natural logarithm of the initial mass divided by final mass. This seemingly simple formula revealed why spaceflight demands such enormous rockets compared to their payloads. To reach orbital velocity, a single-stage rocket would need to be roughly 90% fuel by mass, making multi-stage designs essential. The VFR attracted brilliant minds, including Wernher von Braun, then a teenager fascinated by space exploration. The Society conducted practical experiments at a site called Raketenflugplatz, or Rocket Flight Place near Berlin. Their early rockets were crude devices that frequently exploded, but each failure provided valuable data about combustion dynamics, structural loads, and control systems. Similar organizations emerged elsewhere. In America, the American Rocket Society formed in 1930. Inspired partly by European achievements, these societies served as crucial bridges between theoretical work and practical engineering, fostering collaboration and knowledge sharing that accelerated technological development. The European approach differed significantly from Goddard's methodology. While Goddard worked largely alone, maintaining secrecy about his innovations, European rocket societies embraced open collaboration and public engagement. They published technical papers, held conferences, and actively promoted spaceflight as humanity's inevitable destiny. This openness accelerated progress, but also attracted military attention. By the early 1930s, German military officials recognized rockets' potential as weapons delivery systems. The Treaty of Versailles prohibited Germany from developing traditional artillery and aircraft, but said nothing about rockets, creating a legal loophole that would prove historically significant. The theoretical work of Oberth, Tsiolkovsky, and others established fundamental principles that remain valid today. They calculated orbital mechanics, analyzed propulsion efficiency, and designed mission architectures for lunar and planetary exploration. Their insights about staging, fuel selection, and trajectory optimization became the foundation for all subsequent space missions. Experimental work during this period revealed critical engineering challenges. Combustion instability plagued early liquid fuel engines, causing catastrophic failures. Propellant injection systems required precise engineering to achieve proper fuel oxidizer mixing. Cooling systems became essential as engine temperatures exceeded the melting points of conventional materials. These pioneers also grappled with guidance and control challenges. Early rockets flew ballistic trajectories with minimal control, but Space missions would require precise navigation and maneuvering capabilities. Gyroscopic stabilization, radio guidance, and autonomous control systems emerged as essential technologies requiring development. The interwar period established rocketry as a legitimate scientific discipline. What began as wild speculation about space travel evolved into rigorous engineering programs with defined technical objectives. The convergence of theoretical understanding, practical experimentation, and growing institutional support created conditions for the dramatic advances that would soon follow. The transformation of rocketry from scientific curiosity to military necessity began in 1932 when Captain Walter Dornberger of the German Army Ordnance Office visited the VFR's experimental site near Berlin. What he witnessed, crude rockets achieving modest altitudes amid frequent explosions, might have seemed unimpressive, but Dornberger recognized the technology's potential for military applications. Germany's unique situation under the Treaty of Versailles created an opportunity for rocket development. While prohibited from developing traditional artillery with ranges exceeding 100 kilometers, rockets occupied a legal gray area that German military planners exploited. Dornberger recruited several VFR members, including 20-year-old Wernher von Braun, to develop military rockets at the secret Kummersdorf facility south of Berlin. Von Braun's recruitment marked a pivotal moment in space history. Though motivated by dreams of space exploration, he accepted that military funding offered the only realistic path to developing advanced rocket technology. This Faustian bargain would enable extraordinary technical achievements while serving destructive purposes, embodying the dual nature of rocket technology itself. The German rocket program initially focused on developing liquid-fueled engines with greater thrust and reliability than previous designs. The A-series rockets, beginning with the A-1 in 1933, systematically addressed fundamental engineering challenges. Each iteration incorporated lessons learned from failures, gradually improving performance, reliability, and control systems. By 1937, the program had outgrown Kummersdorf's limited facilities. Construction began on Peenemünde, a massive research complex on the Baltic Sea coast that would become the world's most advanced rocket development center. The facility employed thousands of engineers, scientists, and technicians working on what would become the V-2 rocket, the world's first operational ballistic missile and the direct ancestor of space launch vehicles. The V-2, designated A-4 during development, represented revolutionary technical achievements. Standing 46 feet tall and weighing over 13 tons when fueled, it could deliver a 1-ton warhead across distances exceeding 200 miles. More importantly for space exploration's future, it demonstrated that large liquid fuel rockets could achieve supersonic speeds, reach altitudes above 60 miles, and operate with acceptable reliability. Technical innovations developed for the V-2 became fundamental to all subsequent rockets. The engine generated 25 tons of thrust by burning liquid oxygen and ethyl alcohol, achieving combustion efficiency previously thought impossible. Turbopumps driven by steam generators delivered propellants at precise flow rates and pressures. An inertial guidance system using gyroscopes and accelerometers enabled autonomous flight control. Parallel developments occurred in the Soviet Union, though details remained classified for decades. Sergei Korolev, who would later become the chief designer of the Soviet space program, began developing rocket technology in the 1930s. Like von Braun, Korolev recognized that military applications provided the necessary resources for advancing rocket technology toward eventual space applications. The Soviet approach differed from German methodology in several crucial respects. While German engineers pursued single, sophisticated designs optimized for specific missions, Soviet engineers favored simpler, more robust systems that could be mass-produced and adapted for various applications. This philosophy would later influence Soviet space program strategies and achievements. Both programs faced similar technical challenges that pushed engineering capabilities to their limits. Combustion chamber cooling required innovative solutions as engine temperatures exceeded 2,000 degrees Celsius. Structural designs had to withstand enormous loads during acceleration while remaining light enough for efficient flight. Guidance systems needed unprecedented accuracy to hit distant targets. The war years also witnessed crucial advances in metallurgy, electronics, and manufacturing techniques essential for rocket development. New aluminum alloys provided strength-to-weight ratios necessary for efficient rocket structures. Electronic systems enabled precise control of engine parameters and flight trajectories. Manufacturing processes scaled up from laboratory prototypes to operational production systems. By war's end, both German and Soviet programs had developed operational ballistic missiles, though only Germany had deployed them in combat. The V-2's operational use revealed both the weapon's destructive potential and its limitations as a military system. More significantly for humanity's future, these programs had proven that large, controllable rockets could reach the edge of space, setting the stage for the space age's dawn. The technical achievements of wartime rocket development created the foundation for post-war space exploration. Liquid fuel engines, inertial guidance systems, multi-stage designs, and sophisticated manufacturing techniques developed for military purposes would soon carry humanity beyond Earth's atmosphere. The dreams of Goddard, Oberth, and Tsiolkovsky were approaching reality. As Allied forces advanced into Germany during the war's final months, American intelligence officers raced to capture not just German rocket technology, but the minds behind it. Operation Paperclip, authorized by President Truman, brought over 1,600 German scientists and engineers to America, including Wernher von Braun and his core team from Peenemünde. This controversial program would fundamentally reshape American aerospace capabilities and accelerate humanity's journey to space. Von Braun and his colleagues arrived at Fort Bliss, Texas, in September 1945, carrying technical, documentation and hardware from the V-2 program. Their immediate task involved supporting American efforts to understand and replicate German rocket technology. But von Braun harbored grander ambitions. He envisioned using military rocket development as a stepping stone toward space exploration and eventual human missions to Mars. The American military initially showed limited interest in space applications, focusing instead on developing intercontinental, ballistic missiles capable of delivering nuclear warheads. The emerging Cold War with the Soviet Union created urgent demand for long-range weapon systems, providing funding and political support for advanced rocket development. Von Braun accepted this reality while quietly promoting space exploration through popular articles and presentations. Meanwhile, the Soviet Union pursued parallel objectives under different circumstances. Soviet forces had captured Peenemunde's production facilities and recruited their own group of German engineers, though fewer in number and generally less senior than those acquired by America. More importantly, the Soviets retained Sergei Korolev, whose leadership would prove decisive in early space achievements. The American rocket program relocated to Huntsville, Alabama in 1950, where the Army Ballistic Missile Agency established its headquarters. Von Braun's team began developing the Redstone rocket, America's first operational ballistic missile based on V-2 technology, but incorporating significant improvements. The Redstone featured enhanced range, improved guidance systems, and greater reliability than its German predecessor. Technical challenges during this period required innovative solutions that advanced rocket science significantly. Engine development focused on achieving higher thrust levels while maintaining combustion stability. The Rocketdyne Company, working closely with von Braun's team, developed engines generating over 75,000 pounds of thrust, triple the V-2's capability. Guidance system improvements proved equally crucial. The V-2's inertial guidance system, while revolutionary for its time, lacked the precision required for intercontinental missions or space applications. American engineers developed more sophisticated gyroscopic systems and began investigating radio guidance techniques that would eventually enable lunar missions. The Soviet program advanced along similar technical trajectories, but with different strategic priorities. Korolev's R-7 rocket, developed during the early 1950s, represented a more ambitious approach than contemporary American designs. With over 1 million pounds of thrust from 20 separate engines, the R-7 possessed capabilities far exceeding military requirements, suggesting Korolev's space exploration intentions. Both programs faced fundamental engineering challenges that pushed technological boundaries. Scaling rocket engines to higher thrust levels required understanding complex combustion phenomena that frequently caused catastrophic failures. Structural designs had to support enormous loads while minimizing weight penalties that reduced performance. Manufacturing processes needed unprecedented precision and quality control. The American space program received unexpected impetus from President Eisenhower's commitment to launching artificial satellites during the International Geophysical Year of 1957-58. Project Vanguard, managed by the Naval Research Laboratory, aimed to demonstrate American technological leadership through peaceful space applications. The project's scientific objectives included studying Earth's atmosphere, magnetic field, and radiation environment. Von Braun's team proposed using modified Redstone rockets for satellite launches, but military and political considerations favored the civilian Vanguard program. This decision would soon prove problematic when the Soviet Union achieved surprise space firsts that caught America unprepared. The competition between military and civilian space programs reflected broader tensions about space exploration's proper role and governance. Technical developments during this period established foundations for future space achievements. Multi-stage rocket designs enabled higher velocities than single-stage systems could achieve. Improved propellant combinations increased engine efficiency and specific impulse. Advanced materials withstood extreme temperatures and pressures encountered. During spaceflight, the transformation of former weapons engineers into space exploration pioneers embodied the era's complex moral landscape. Men who had developed instruments of destruction now worked toward humanity's greatest adventure, though the military applications of their work remained prominent. This duality would characterize the space program throughout the Cold War period. By the mid-1950s, both American and Soviet rocket programs possessed capabilities approaching those required for spaceflight. Engines generated sufficient thrust, guidance systems achieved necessary precision, and manufacturing processes could produce reliable hardware. The stage was set for humanity's first tentative steps beyond Earth's atmosphere. At 7:33 Moscow time on October 4, 1957, a modified R-7 intercontinental ballistic missile lifted off from the Baikonur Cosmodrome in Kazakhstan, carrying a gleaming aluminum sphere weighing 184 pounds. Sputnik 1, Russian for traveling companion, became humanity's first artificial satellite, orbiting Earth every 96 minutes while transmitting radio signals that announced the space age's dawn to a stunned world. The basketball-sized satellite represented far more than a technological achievement. It fundamentally altered global perceptions of scientific capability and national prestige. Sputnik's radio beeps, easily received by amateur operators worldwide, provided undeniable proof that the Soviet Union had achieved what many considered impossible. The psychological impact resonated particularly strongly in America, where confidence in technological superiority had been a cornerstone of national identity. American reaction mixed disbelief, fear, and determination. If Soviet rockets could place satellites in orbit, they could certainly deliver nuclear warheads to American cities. The military implications seemed clear, but the scientific and exploratory possibilities captured public imagination even more powerfully. Within hours of Sputnik's launch, American newspapers were demanding explanations for how the Soviet Union had achieved such a dramatic space first. The American satellite program faced immediate pressure to respond quickly. Project Vanguard, originally conceived as a measured scientific endeavor, suddenly became a matter of national urgency. However, the program's first launch attempt on December 6, 1957, ended in spectacular failure when the rocket exploded shortly after liftoff, earning the humiliating nickname Kaputnik in newspaper headlines. Wernher von Braun's team at Huntsville received emergency authorization to proceed with their satellite proposal using a modified Jupiter C rocket, essentially an upgraded Redstone. Working with unprecedented urgency, they prepared Explorer 1, America's first satellite, which launched successfully on January 31, 1958. Though weighing only 31 pounds compared to Sputnik's 184, Explorer 1 achieved a crucial scientific breakthrough. Explorer 1 carried instruments designed by James Van Allen of the University of Iowa to study cosmic radiation in space. The satellite's elliptical orbit, ranging from 224 to 1,563 miles altitude, revealed the existence of radiation belts surrounding Earth. These Van Allen belts, as they became known, represented space exploration's first major scientific discovery and demonstrated that satellites could serve important research purposes beyond mere technological demonstration. The discovery of radiation belts had profound implications for future human spaceflight. The trapped charge particles posed potential health risks to astronauts and could damage sensitive electronic equipment. Understanding this radiation environment became essential for designing spacecraft systems and mission profiles that would protect human crews during extended spaceflights. Soviet successes continued with dramatic regularity that maintained their early momentum. Sputnik 2, launched November 3, 1957, carried Laika, a dog, becoming the first spacecraft to transport a living creature to orbit. Though Laika died within hours due to overheating, the mission demonstrated that biological organisms could survive launch stresses and initial orbital conditions, paving the way for human spaceflight. The American response involved both technical and organizational changes that would define the space program's future structure. President Eisenhower signed the National Aeronautics and Space Act in July 1958, creating NASA as a civilian agency responsible for peaceful space exploration. This decision reflected American values emphasizing scientific research over military applications, though military space programs continued under separate auspices. NASA's formation brought together disparate research organizations under unified leadership focused specifically on space exploration. The agency inherited facilities, personnel, and ongoing projects from the National Advisory Committee for Aeronautics, Army Ballistic Missile Agency elements, and Naval Research Laboratory components. This consolidation provided resources and expertise necessary for ambitious space missions. The Soviet Union achieved the next major milestone on September 14, 1959, when Luna 2 became the first human-made object to reach the Moon's surface. Though the spacecraft crashed rather than landed softly, it successfully delivered Soviet pennants to the lunar surface and confirmed that space missions could achieve interplanetary distances. Luna 3 followed in October, photographing the Moon's far side for the first time in history. American lunar missions began with the Pioneer program, though early attempts encountered frequent failures that highlighted the enormous technical challenges of deep space missions. Pioneer 1 through 3 failed to achieve their intended trajectories, demonstrating that extending rocket capabilities from Earth orbit to lunar distances required significant technological advances and operational improvements. The period's most stunning achievement occurred April 12, 1961, when Yuri Gagarin completed one orbit of Earth aboard Vostok 1, becoming the first human being to travel in space. Gagarin's flight lasted 108 minutes and demonstrated that humans could survive launch accelerations, weightlessness, and re-entry forces without serious adverse effects. His safe return proved that human spaceflight was feasible, not merely theoretical. American efforts to match Soviet achievements culminated in Project Mercury, which selected 7 test pilots as astronauts in April 1959. The Mercury program aimed to place American astronauts in orbit using Atlas rockets, modified intercontinental ballistic missiles similar to the Soviet approach. However, conservative design philosophy and extensive testing protocols meant American human spaceflight would lag significantly behind Soviet achievements. The space race had fundamentally transformed from technological competition to geopolitical contest with global implications. Both nations recognized that space achievements demonstrated scientific capability, technological sophistication, and national determination. The stakes extended far beyond scientific discovery to encompass international prestige and ideological credibility during the Cold War's most intense period. President John F. Kennedy's address to Congress on May 25, 1961, transformed space exploration from scientific endeavor to national crusade with a single audacious declaration. I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. This commitment, made just 3 weeks after Alan Shepard's suborbital flight, launched the most ambitious technological undertaking in human history. The moon landing goal seemed nearly impossible given America's space capabilities in 1961. Soviet achievements continued demonstrating significant technical advantages, including longer duration flights, multiple crew missions, and spacewalk capabilities that America had yet to attempt. The scale of technological advancement required to reach the moon within 8 years would demand unprecedented resources, innovation, and national commitment. NASA's response involved developing Project Apollo, a comprehensive program encompassing every aspect of lunar missions from launch vehicles to life support systems. The program's centerpiece became the Saturn V rocket, standing 363 feet tall and weighing over 6 million pounds when fully fueled. This massive vehicle generated 7.5 million pounds of thrust from its first stage alone, equivalent to the power output of 85 Hoover dams. Wernher von Braun's team at the Marshall Space Flight Center designed the Saturn V, using clustered engine configurations that provided both enormous thrust and redundancy for crew safety. The first stage employed 5 F-1 engines, each generating 1.5 million pounds of thrust, while burning refined kerosene and liquid oxygen at a rate of 3 tons per second. These engines represented remarkable engineering achievements, requiring innovative solutions for combustion stability and cooling. The technical challenges of lunar missions extended far beyond launch vehicle development. NASA had to master orbital rendezvous and docking, develop life support systems for multi-day missions, create navigation systems capable of guiding spacecraft across 250,000 miles, and design heat shields that could protect returning crews from lunar re-entry velocities exceeding 25,000 miles per hour. Project Gemini served as Apollo's crucial stepping stone, testing techniques and systems essential for lunar missions. Gemini spacecraft carried 2-person crews for extended duration flights, demonstrated orbital maneuvering capabilities, and pioneered spacewalk procedures. The program's 10 crewed flights between 1965 and 66 proved that astronauts could work effectively in space for the weeks required for lunar missions. Meanwhile, the Soviet lunar program struggled with technical and political challenges that would ultimately prevent them from matching American achievements. The massive N-1 rocket, designed to compete with Saturn V, suffered from engine clustering problems and inadequate testing that resulted in 4 consecutive launch failures between 1969 and 72. Political infighting and resource constraints further hampered Soviet progress toward lunar landing capabilities. Apollo 8's lunar orbit mission in December 1968 demonstrated that NASA had mastered the navigation and life support challenges of deep space flight. The crew's Christmas Eve broadcast from lunar orbit, reading from the Book of Genesis, while Earth appeared as a small blue marble against the lunar horizon, provided one of the most profound moments in human history and proved that lunar landing missions were technically feasible. The final technical hurdle involved developing and testing the lunar module, the specialized spacecraft designed to land on the moon's surface. This strange-looking vehicle, optimized for vacuum operation rather than atmospheric flight, had to function perfectly on its first operational use. Apollo 9 tested the lunar module in Earth orbit, while Apollo 10 conducted a full dress rehearsal that approached within 50,000 feet of the lunar surface. Apollo 11's historic mission began July 16, 1969, when Saturn V vehicle number 506 lifted Neil Armstrong, Buzz Aldrin, and Michael Collins toward lunar destiny. The mission's success required flawless performance from millions of components, precise navigation across interplanetary distances, and split-second decision-making during the lunar landing sequence when computer alarms threatened to abort the Attempt Armstrong's manual piloting during the final landing phase exemplified the human element that made lunar missions possible. With fuel running dangerously low and computer warnings continuing, he guided the Eagle to a safe landing in the Sea of Tranquility with less than 30 seconds of fuel remaining. His famous words, "The Eagle has landed," announced humanity's greatest exploration achievement to the world. The moon landing represented the culmination of engineering excellence, scientific understanding, and human courage that began with Goddard's first liquid-fuel rocket 43 years earlier. Over 400,000 people contributed to Apollo's success, creating technologies that revolutionized computing, materials science, telecommunications, and countless other fields. The program demonstrated that seemingly impossible goals could be achieved through sustained commitment and technical excellence. Apollo's success vindicated the vision of early rocket pioneers who dreamed of space exploration despite widespread skepticism. Goddard, Aubert, and Tsiolkovsky had correctly predicted that rocket technology would enable human spaceflight, though none lived to witness lunar landings. Their theoretical insights and experimental work provided the foundation for humanity's greatest adventure. The moon landing also marked a transformation in space exploration's character and objectives. What began as Cold War competition evolved into scientific endeavor that revealed new perspectives on Earth's place in the cosmos. The iconic Earthrise photograph, showing our blue planet rising above the lunar horizon, fundamentally changed how humanity viewed itself and our planetary home. 6 successful lunar landing missions between 1969 and 72 brought 12 astronauts to the moon's surface, where they conducted scientific experiments, collected samples, and explored terrain that had remained unchanged for billions of years. Their achievements proved that human space exploration could yield profound scientific discoveries while inspiring generations to pursue seemingly impossible dreams. The decade following Apollo's lunar triumphs witnessed a fundamental shift in space exploration philosophy, from spectacular one-time achievements to sustainable, cost-effective operations. NASA's Space Shuttle program, approved by President Nixon in 1972, embodied this new approach by developing the world's first reusable orbital spacecraft system. The shuttle's revolutionary design promised to reduce launch costs dramatically, while enabling routine access to low Earth orbit. The Space Shuttle system represented engineering compromises that reflected political and economic realities rather than pure technical optimization. Unlike expendable rockets that discarded expensive components after single use, the shuttle's main engines, solid rocket boosters, and orbital vehicle were designed for multiple missions. This reusability concept seemed economically attractive, though operational experience would reveal complexities that limited cost savings. Shuttle Columbia's first flight on April 12, 1981, exactly 20 years after Gagarin's historic mission, inaugurated a new era of space operations. The successful 2-day orbital mission demonstrated that winged spacecraft could launch like rockets and land like airplanes, providing unprecedented flexibility for deploying satellites, conducting experiments, and servicing orbital facilities. The shuttle program's most significant achievement involved constructing and maintaining the International Space Station, or ISS, humanity's most ambitious space project. This orbital laboratory, involving partnerships between America, Russia, Europe, Japan, and Canada, demonstrated that former adversaries could collaborate on peaceful space exploration. The station's continuous human presence since November 2000 represents the longest duration human space mission in history. Meanwhile, the Soviet Union continued developing expendable launch vehicles that prioritized reliability and cost-effectiveness over reusability. The Soyuz rocket family, evolved from Korolev's original R-7 design, became the most successful launch system in history, with over 1,800 flights and a remarkable safety record. This conservative approach proved prescient, as reusable systems demonstrated greater complexity and cost than initially anticipated. The shuttle program's tragic losses, Challenger in 1986 and Columbia in 2003, highlighted inherent risks in human spaceflight and prompted renewed emphasis on crew safety. These accidents, while devastating, led to improved safety protocols, better risk assessment procedures, and enhanced crew escape systems that benefited all subsequent human spaceflight programs. Commercial spaceflight emerged as a transformative force during the early 21st century, led by companies like SpaceX and Blue Origin, founded by entrepreneurs who grew up inspired by Apollo achievements. These organizations brought fresh perspectives to rocket design, manufacturing processes, and operational procedures that challenged traditional aerospace industry approaches. SpaceX's Falcon 9 rocket, first launched in 2010, demonstrated that private companies could develop reliable launch vehicles while dramatically reducing costs through innovative design and manufacturing techniques. The rocket's first-stage recovery and reuse capability, achieved through precision landing technology, finally realized the cost reduction promises that had motivated shuttle development decades earlier. The Falcon Heavy, essentially 3 Falcon 9 first stages strapped together, created the world's most powerful operational rocket when it debuted in 2018. Its successful demonstration flight, which launched Elon Musk's personal Tesla Roadster toward Mars orbit, captured global attention and demonstrated that private companies could achieve capabilities rivaling government space programs. Blue Origin's New Shepard vehicle pioneered commercial human suborbital flight, providing paying customers brief experiences of weightlessness and views of Earth's curvature. This achievement fulfilled dreams of space tourism that visionaries had predicted since the 1950s. Though costs remain high enough to limit participation to wealthy individuals, contemporary rocket development focuses increasingly on Mars exploration and eventual human settlement. SpaceX's Starship system, under development since 2019, aims to transport large crews and cargo loads to Mars using fully reusable vehicles that could enable self-sustaining human colonies on other worlds. These ambitions echo the visions of early space pioneers who saw space exploration as humanity's destiny. International cooperation has become increasingly important as space exploration costs and complexities exceed individual nations' capabilities.